the last video, we derived this recurrence relation for the Tower of Hanoi recursive algorithm. So let's analyze this, and let's try to figure out how many moves does this actually take. So before we get into the guts of the analysis, it's always worth looking at a recurrence relation and saying, what do I expect to see out of this? So basically, what's happening here is we're shrinking the input size just a little, right? Right, a small shrinkage of input size, right? Small reduction. And we're recursing twice. Okay, and so you'll develop intuition for this over time, but this should start to worry you just a little bit. That, suppose n is 10, then what's going to happen on our first recursive call? We're going to say, let's move n disks. We can't do that. We got to move 9 disks. So we move 9 disks twice, and then proceed. And then on our next recursive call, we'll move 8 disks 4 times. And then on our next recursive call, we'll move 7 disks 8 times, right? And so the number of recursive calls is going to increase exponentially, while the size of the input is shrinking quite slowly. And so this suggests that maybe it's going to take a lot of moves to move a large stack of disks. So let's chase this recursion through, solve it, and actually figure out the answer. So I'm gonna follow my program that I love so much, and I'll say here's my t of x. So t of x is 2 t of x minus 1 plus 1. And so for x equals n minus 1, right? So we're solving the first case that we see right here. Then we'll be able to derive an expression for t of n minus 1. And so t of n minus 1 then is 2 times t of n minus 1 minus 1 plus 1. And I won't go into those details again, but this ends up being 2 t of n minus 2 plus 1. Okay, so the question here that this recurrence is getting at is, how many moves does it take to move a stack of n minus 1? Well, first you have to move a stack of n minus 2, then you move a disk, then you move another stack of n minus 2. Okay, so this is completely consistent with the algorithmic approach that we've established prior. All right, so let's plug this back in, and we get t of n first could be equal to 2 t of n minus 1 plus 1. Yeah, but it could also be equal to 2 times 2 of t of n minus 2 plus 1 plus 1. Okay, so this plus 1, right, this whole piece here came from that, and this plus 1 came from above. Okay, so bookkeeping is key with this, as I will continue to harp on. Make sure that you have your parentheses in the right spot and that you're not mixing terms. So we'll simplify and then do one more step. So what do we have here? We have 4 t of n minus 2 plus 2 plus 1. Okay, so onward. Let's come up with an expression for t of n minus 2. And so t of n minus 2 is going to be 2. So this is letting x equal n minus 2. So t of n minus 2 is 2 t of n minus 3 plus 1. And so in the next step here, and I'm just going to simplify things, myself. In the next step here, what we have is 8 t of n minus 3 plus 4 plus 2 plus 1. Okay, and so this is quite different from some of the recurrence relations that we've analyzed, at least in the videos so far. But the pattern now should be clear, right? This is k equals 1 up here. Here's k equals 2. Here's k equals 3. We've got 2 to the k. We've got k. And then here we have k terms, right? So k terms. And those terms can be expressed as sums of powers of 2. Okay, so our pattern in the end is going to be 2 to the k times t of n minus k plus, and then this is a sum, and the sum should have exactly k terms in it, right? So one way to have exactly k terms in it is like this. I'll set up a sum from I equals 0 to k minus 1. Right? And so before we actually fill in the blank here, what do we know about this sum? We know this sum has exactly k terms in it, right? And that much is clear. That's what's required, right? There's k terms in the sum above, k terms in this summation here. So there's k terms in this sum, and the sum is 2 to a power, right? So what should we have here? Well, this is 2 to the 0, this is 2 to the 1, this is 2 to the 2. So you know, when k equals 3, the first thing here should be just, you know, 2 to the 0, and I here starts at 0. So we're in good shape. So this is 2 to the I. So it's worth you know, writing, if you don't believe me right off the bat, it's worth writing out several terms of this sum and making sure that this is what's actually happening, right? Convince yourself that this is the right expression for the above recurrence, because you know it's important to be able to generate these things as you go forward. Okay, so what do we have here? Well, you know, we can simplify this. This is a geometric series, so we can put this in terms of a closed form, right? We don't have to leave it in terms of the sum. And so what does that look like? Well, let me leave these ones alone. So 2 to the k times t of n minus k. And now plus 2 to the k minus 1 over 2 minus 1. Okay, and that's a formula that I gave you at some point. It's a formula you can look up for the geometric series. But this is something that if you don't memorize, you should at least keep handy somewhere, right? This is something useful. So now what about our anchoring step? Well, we know t of 1. Right? And in here we have t of n minus k, so t of n minus k. So we want to solve 1 equals n minus k. And so, you know, to put this in terms of k, we have k equals n minus 1. So now let's just plug those in over here and see what we get. So, you know, insert or substitute these in, and we have 2 to the n minus 1 times t of 1 plus 2 to the n minus 1 minus 1 over 1. And I'll just simplify that and erase it. Okay? And so, you know, what does this come out to? Well, I've got 2 to the n minus 1 plus 2 to the n minus 1. What happens when you do that? Well, you know, 2 to the n minus 1 plus 2 to the n minus 1 minus 1 equals 2 times 2 to the n minus 1, right? There's 2 of those. So this is, and I'm going to just go into the gory details here. This is 2 times 2 to the n minus 1 minus 1. And, you know, if you want, you could think about it like this. This is 2 to the power of 1 times 2 to the power of n minus 1. If I ever have this product like this, you know, where I have the same base raised to some powers and I have the product of those two numbers, the way I combine the powers is I just add the powers. So altogether, this is 2 to the n minus 1. Okay, and so sure enough, like our intuition when we kind of did the spit check on the recurrence relation suggested, sure enough, we have a very slow algorithm. So we require exponentially many moves. So this is big theta of 2 to the n, right? So exponentially many moves. And so here's a lesson you can learn from the Tower of Hanoi, is when we began this, we started with a very simple looking algorithm, right? It just had 2 recursive calls. The recursive calls were on something simple and easy to wrap your head around. And what it gave us was this horrifyingly slow, massive number of move algorithm. And so the word of caution that this should give you is that, you know, if just because you have a simple algorithm does not mean that it's a fast algorithm. All right. You know, sink your teeth into this. get familiar with kind of the concept of what's happening here. Draw yourself a recursion tree if you like, or solve a bigger problem by hand if you like, to kind of get a feel for what it means to have exponential time algorithm.